Okay. Hope you are able to see the whiteboard which I'm sharing with you right now. So I'm going to take as it we have defined the linear transformation as it is given, as it is mentioned. I'm going to do the first problem, example number 1 in my class, but in the book you will get it in the uh, second page, third page, which is given as example 3, and the transformation is given by t from the space two-dimensional space R2 to R2 by t of a1 comma a2, which is a1 minus a2. Okay. Now this transformation is also very important transformation in the sense that it has a geometrical significance. What is the geometrical significance of this transformation? This transformation, let me draw it, you will understand. So this is my, consider this as my y-axis, this is my y-axis, or you can say at a2 axis, whatever, and this is my x-axis, positive. I'm taking the positive quadrant, and suppose this point is what, a1 comma a2, and this is the point and this is the coordinate, and this is the vector starting from the origin. Okay. Now you consider this particular x-axis, positive direction of x-axis from 0 to x, you consider this to be your mirror. This is a mirror, consider, and this particular point is standing in front of the mirror. What will happen? This particular point is going to see its reflection. This particular point is going to see its reflection, and in this case the reflection of the point here will be a1 minus a2. Okay, so your this distance from origin to the point is same. This distance is a1 for both the case. This distance is a1. For this distance is a2, and that distance is minus, you can consider it as minus a2. So your right hand becomes your left hand, your left hand become your right hand in front of the mirror, and therefore, but your distance remain the same from the if you are standing over here, your distance from the mirror remains same in the real world as well as in the virtual world. Okay. This particular, as you can see in the book, this particular transformation as it is given, this transformation is called reflection transformation. It is known as reflection transformation, and they have mentioned that this reflection transformation is linear transformation. So I am going to use property number 4, that is the last property, to solve this particular problem. I'm going to prove that yes, indeed, this reflection transformation is a linear transformation. So let us see how to solve it. Okay. So let us start the proof or solution of the given problem. Here you have to see one thing: whenever you start solving a particular problem, you have to analyze the problem properly, and you have to correlate the problem with the given definition or given theorem. What that to see when a particular electrician comes to your home, and he, before starting his work, what does he see? He tries to see that every setup is okay, the setup is okay, the tools are all right, system is okay. Then he decides that yes, now I can work on it. So here also you have to satisfy yourself, this is actually mm, going according as the definition, as given in the definition. Okay. So you see, two vector spaces actually have been considered over here. One is V and another is W, but here actually the two vector spaces are same. V and W are same. So actually I am defining a linear transformation from V you can say it is a linear transformation from V to V, where V and W are same. Okay, and that is equal to R2. This V and W is equal to R2, the two-dimensional space. Okay, now you know that in two-dimensional space R2, the points are actually of this form: a1 comma a2, two-dimensional points with coordinates a1 and a2, and a1 comma a2 are scalar quantities, and the scalar here, the field capital F, they are, the capital F is the set of real numbers. In the definition of the linear transformation, it was mentioned that the two vector spaces must be vector spaces over the same field. Now, since your vector spaces are same, so this is the vector space over the field R, you know, so this is also a vector space over the field R. So that condition is also being satisfied. So after that, now you can work on it. So what am I going to do? I am going to use this result. Remember, to show that something is linear, some transformation is linear, I am going to use this result. T of a1 x1 plus a2 x2, this is equal to a1 into T of x1 plus a2 into T of x2. Okay, so let us choose 2 points. Let us choose 2 points x comma y in R2. And since they are in R2, so the form of x is a1 comma a2, and the form of y is also b1 comma b2. Okay, right? And you can write for clarity that ai comma bi belonging to capital R, where I is from 1 to 2. Okay, now we select two scalar quantities a comma b in R, and I am going to show that T of x plus y is equal to tx, sorry, I am going to show that T of ax plus by, this is equal to a into tx plus b into ty. If I can show this, our job will be done. Okay, so let us write it. Left hand side is T of a into x plus b into y, and this is equal to T of a into a1 comma a2, because my x is a1 comma a2, the coordinate of x, and b into b1 comma b2. Okay, and this is actually equal to a1 comma a2, because you already know the scalar multiplication, and this is equal to b1 comma b2. Okay, and we can write it as, by coordinate wise vector addition, we can write it as a1 plus b1 comma a2 plus b2. Okay, you got my point? So we can write it as this a1 plus b1 and a2 plus b2. But you already know that the transformation is given by the following formula: T of a1 comma a2 is equal to a1 comma minus a2. Okay, this is my formula given. So I can write it as, this is your first coordinate, it will remain same. So a1 plus b1, this will remain same, and that will become, the second coordinate will become minus of that, a2 plus b2. Why? Because in this case, this is your first coordinate and that is your second coordinate. First coordinate remains same, second coordinate is preceded by a minus sign. So we can write it as a1 plus b1 comma minus a2 minus b2. Now you see, by using the coordinate wise vector addition, I can separate this particular thing in the following manner. I can write it as a1 minus comma minus a2 plus b1 comma minus b2. Okay, and by the given rule I can write it as, yeah, I can also write it as, by scalar multiplication property I can take a common and I can write it as a into a1 comma minus a2 plus we can take b common and we can write b into b1 comma minus of b2. But you know that t of a1 a2 is a1 minus a2, so we can write it as a t of a1 comma a2 plus b t of b1 comma b2 by definition of the transformation. And you know that a1 comma a2 is nothing but your x vector and b1 comma b2 is nothing but your y vector, and you see we have got RHS. So from this we can write that reflection transformation is a linear transformation. Reflection transformation is a linear transformation. So whenever you stand in front of a mirror and whenever you look into your image, as now as I can see on my video too on the screen, so this video of mine is my real, I'm moving my hand like this, so my reflection is also moving inside the camera. So the thing as I'm sitting from a with a specific distance from my laptop, my virtual image is actually equidistant from the mirror as I am, but we are not able to guess it because this I'm actually dealing with the two-dimensional system. If I can project the three-dimensional image of mine, you would be able to see the distance properly. We already know this from our experiences of physics. But what you are going to, as you can see yourself, I can see myself, these all are our reflections on the mirror, and the reflections which I am actually seeing is actually defined by this reflection transformation. Since this transformation is valid, so I am able to see my reflection. Or you can say my reflection that I'm seeing right now in front on the mirror is mathematically defined in the following manner. In the previous cases, we all only discussed about the physics of the thing, but right now we are giving a particular term to the physical uh, significance. I'm giving it a name. I'm saying that reflection is not just a matter of physics now. It has become a matter of mathematics also. And by mathematics language, how will, if you want to translate the knowledge of your physics in terms of mathematics, what will be written in terms of the mathematical language? And this is the thing which I have obtained. So this is the mathematical statement of the reflection, the well-known reflection property which has already been dealt in physics. Okay, so reflection is a linear transformation. Okay, next I can show you another problem, example number 2 in my case, and in book it is given as example number 4. It is given by the transformation is given by t from R2 to here. Also they have collected the same vector space, and it is defined as t of a1 comma a2, that is equal to a1 comma 0. And if you want to draw its figure, you can do it by yourself very well right now. You know that this particular thing is nothing but a point a1 comma a2, and I am projecting it over here. So we can term this operator, this transformation as, we can term this transformation as projection transformation, projection. Okay, you also know this particular term from your knowledge of physics. So I'm going to show that this transformation is a projection transformation. So I'm going to apply the rule once again. So solution is that, let us select 2 points x comma y in R2, so that x is equal to a1 comma a2 and y is equal to b1 comma b2, and ai bi belonging to R, I equals to 1 to 2. Then if we select two scalars C and D, let us name it in a different way, C and D in R, then T of Cx plus dy, that will be equal to T of C into a1 comma a2 plus D into y b1 comma b2, and we can write it as T of ca1 comma ca2 plus db1 comma db2, and then we can treat it as T of ca1 plus db1 ca2 plus db2. And you know that in the, according to the following transformation, your first coordinate remains same, but second coordinate is projected to 0. So if I apply to this, this is the first coordinate and this is the second coordinate, I can write it as ca1 plus db1 comma 0. Now we can separate this in the following manner. I can write it as ca1 plus db1 and this as 0 plus 0. Remember, this 0 is a scalar 0. This 0 is a scalar 0, which is not a vector 0. So it is actually a scalar 0, which is taken from the set of real numbers. That is our usual 0. So I can now separate it in the following manner. I can write it as C1 0 plus DB1 0. And you know that this is nothing but equals to T of, we can also write it as, we can take, we can call it as CA1 comma C into 0 plus DB1 comma D into 0. We can write it to, because when a scalar quantity, non-zero scalar quantity is multiplied by the zero scalar quantity, then the result is 0. So I'm writing over here. So that becomes, this is equal to CA1. I can take the C common. I can take C outside because it is actually done, because scalar multiplication of coordinates is done in the following manner. And I can take D also outside. We can get D of B1 0, and therefore C A1 0 can be written as T of A1 comma A2, and B1 0 can be written as T of B1 comma B2, and therefore we can write it as C into T of X plus D into T of Y, and therefore this implies T is linear. This implies T is linear. Okay, so you see that actually we have also shown that this projection operator is also a kind of linear operator. Projection operator is also a kind of linear operator. And if you can see, I am leaving it for you to solve by yourself. If you, I am showing you the diagram. If you consider this diagram, say suppose I'm considering this vector, which I name it as a1 comma a2. Okay, and this vector is making an angle This vector is making an angle alpha with the positive direction of x-axis, and I am moving this vector further anti-clockwise manner. So I am giving it, it is actually making an angle with the original vector as this. The angle is theta, and with the positive direction of x-axis, it is making an angle theta plus alpha. This vector is actually called rotation. This transformation t theta is actually called rotation transformation t theta. And this rotation transformation, this has been beautifully explained in the book as an example 2. And the rotation transformation is given as t theta a1 comma a2. You will, if you read it, you will understand. It is a beautiful example. The transformation is given by this a1 cos theta into a2 sine theta minus a2 sine theta and a1 sine theta. Just a minute. What has happened? Okay. So this is a1 sine theta plus a2 cos theta. This transformation they have shown that how they have got this transformation. It is shown in the book. Okay. So your job is to show that this transformation, which we call as rotation transformation, that is also linear. This rotation transformation is also linear. Now you see the beauty of this particular exercise is that now suppose you can move, you can see the cursor movement. I am moving a cursor, and with this cursor I am going to draw straight lines or curves or points like this. So let us draw a point over here. This is a point. Now this point, if I call this as a point, okay, so this is my point. As you can see, all of you can see, I do not know what will be its direction. I do not know whether I'm going to make it in the slanting way, or I am going to increase the vector in a upward direction, or in the right hand side direction, or in the below. I don't know. This has infinitely many directions on all sides. Okay, so actually the point is remaining same if I do not do anything. So that actually is being reflected by the zero transformation. This point is not zero transformation in sorry, the identity transformation. In identity transformation, what happens? Not zero transformation, identity transformation. Why? Because in identity transformation, what is happening? You are applying it and the point is remaining same. Okay, so it is actually I of 0 0 is actually 0 0. But if you want to draw, a straight line or something like that, what you do? You first of all you elongate it. If you elongate this particular straight line, and then you move your cursors in this particular manner, so you are actually, your horizontal position was this. And if you consider this virtually, that this was my position, with respect to this position I am moving my straight line in the anti-clockwise direction like this. So with my earlier position, this particular straight line is making some angle. So how this particular movement is happening? This particular movement is happening because rotation transformation is defined. And the transformation which is shown over here, whenever in Microsoft Excel or in this particular whiteboard, I am able to move this cursor in the following manner, because inside behind the screen, the algorithm for this transformation has been written. A computer algorithm for this transformation has been written behind the screen, and therefore I am able to move this cursor in the following manner. If this is done in Microsoft Paint or in this particular whiteboard, you can do it in Excel also. Okay, nowadays it is also done in Word also. So we are able to do it because this transformations algorithm for this transformation has been defined behind the screen. And this transformation is a linear transformation. If the transformation is not linear transformation, what will happen? If you ask me that what is the connection with the linear transformation? Suppose I'm selecting this cursor as you select from the paint, and suppose this transformation is not linear transformation, but when I'll move the straight line, when I'll move it, I move it in this manner. Okay, what will happen? After I release my cursor, that will become a curve, that will become a non-linear thing. Kind of, if I select this, whether I don't know whether I'll be able to show it in whiteboard or not. Say for example, when I'm drawing it like this, it would be quite I'm not able to show it properly over here. If it was Microsoft Paint, I could have shown you. If I select a curve like shapes, and if I try to draw a straight line, it will never be a straight line, because if I when I move it, that that becomes a curved, probably you have seen it. If I select the curved shape, and if I want to draw a straight line, that will never happen, going to happen. If I elongate it in any direction, and if I rotate it and leave it, then it becomes curvilinear. So there the algorithm has been actually different. Okay, different set of algorithms have been used. But when I select this linear thing, I can move it in any direction, clockwise or anti-clockwise manner. So this is actually linear transformation. Okay, so everything is happening because this two-dimensional, what is the logic behind this two-dimensional portal on which I am writing? This is an R2 space, and R2 space, this sort of transformation, a linear transformation, can be defined. A linear transformation like rotation can be defined, linear transformation like projection can be defined, linear transformation like reflection can be defined. And therefore whatever you are seeing right now, whatever tools I'm using right now, all because these things are linear, and therefore I'm able to show it whenever I'm writing. And one important thing I must tell you, whenever I'm writing this, the t of a1 x1 plus a2 x2 is equal to a1 into t1 t of x1 plus a2 into t of x2, you just do not think that it is very easy. It's physical significance. It has a tremendous amount of physical significance, in the sense that, suppose you know that nowadays we actually are dependent on internet, and internet lines are actually going beneath it has been there beneath the transatlantic ocean. Okay, transatlantic channels are there through which the internets we are globally connected with one another. Okay, now each minute many items each minute many items are being sent, images are being sent, photos are being uploaded. You are WhatsApping your friend, I am WhatsApping to my colleague, many things. So many such signals and many such things are actually moving through that transatlantic channel. Okay, but none is cutting another, none is intersecting another. Okay, none is disturbing another. Why is it so? Because all these movements which is happening inside beneath the transatlantic channel, through the transatlantic channel, this movement is linear. This movement is linear, and therefore none is disturbing the other. If they were non-linear, then the scenario could have been different. So linear transformation is very important in this particular case. Okay, and they have shown in the book, there is another problem shown, that if we consider a transformation like this, say for example m cross n, you know that it is the set of all matrices of order m cross n. I am considering a transformation from this set to that set, where number of rows is becoming number of columns and number of column is becoming number of rows, by capital T of A, which is defined as A transpose. This is transpose of A. Okay, then you see, this is also very interesting to see that capital A, this matrix, will belong to this vector space, and the transpose of this matrix will belong to that vector space. Here you see this problem is different, because here the vector space V and vector space W, they are different, they are not same. Okay, this is your vector space V and that is your vector space W. So if I consider this particular example also, you can show that this transpose operation is also a linear operation. So actually what for this you are supposed to take two scalar quantities, say what shall I say for example small p and small q. from the set capital F, which is filled, which can be real number set or complex number set, whatever. And we are going to select two matrices, capital A and capital B, from the set M cross N F. Okay, so that by definition A transpose and B transpose, they belong to the vector space Mn cross n Mf. Okay, if it is so, then you are supposed to show that T of P into A plus Q into B, that will be equal to P of TA plus Q of TB. Okay, if you can show, prove it. If you can show, then your transformation is linear transformation. So transpose operation is also a kind of linear transformation. Then they have defined another example. They have defined another example from, say, for example, another transformation from Pn R to P of Pn minus 1 R. What is this? This is the set of all polynomials, or vector space of all polynomials of degree less than or equal to n, and this is polynomials of degree less than or equal to n minus 1. How they have defined this transformation? What will be the element of this? Element of this particular vector space will be fx, because it is a polynomial. Okay, so of degree less than or equal to n. So when I put this inside the transformation T, we actually get f dash x, or you can say that ddx of x, ddx of fx. Because you know, whenever you consider fx to be x squared is a second degree polynomial, and if you consider f dash x, we get twice x, so its degree is actually becoming lesser. So if x squared is a member of x squared is a member of the set P2R, and this x is actually a member of P1R. Okay, so therefore this transformation, we have done lots of problems on this particular transformation, and probably we have written also this kind of thing, ddx of fx plus gx, ddx of fx plus gx is equal to is equal to ddx of fx plus ddx of gx. Okay, many a times in earlier in school you have used this kind of transformation. Carefully observe that in place of ddx we have t, so that actually become t of fx plus gx, it becomes t of fx plus t of gx. Okay, so you can show that this transformation, that differentiate the property of derivative, the property of derivative is also linear. This property, linear property of derivative, is called linear property of derivative. It is also linear. Okay, it is also a kind of transformation. And lastly, before I conclude my today's session, after this session I'm not going to rejoin because I'm extremely tired. In example 7, they have mentioned, consider that the vector space CR. What is that vector space? Have I seen that vector? Have I seen this particular vector space? Answer is yes. If you have done the exercise, previous exercises, you have seen it, otherwise not. This particular set has been defined in the exercise of subspaces. What is that? This is the subspace. This is the subspace, or every subspace, you know, every subspace is actually a vector space. Okay, so this is a subspace of all continuous real valued function, all continuous real valued function. Okay, so this particular set has been considered. Vector space have been it is also mentioned in the definition in the example 7 also. And let us not call it a subspace, let us call it as a vector space, because because the subspace will be, let us call it as a vector space. First of all, the subspace will be if it is a vector space, its subspace will be CNR. CNR will be the subspace of CR. What is CNR? CNR is also a set of all continuous real valued function having nth derivative. Okay, so that will be the subspace of that. So if this is the vector space of continuous real valued functions, and if I consider two scalars a comma b belonging to R, where a is less than b, we define a transformation from V to R. We define a transformation from V to R. Why R is the, you are consider, you probably you are thinking that it is that if in defining a transformation, we actually consider two vector spaces, okay, T from V to W. And often we considered R, often is considered R as field, okay. Now here the transformation has been defined from, here the transformation has been defined from V to R. Now V is a vector space. What is R? How can R be a vector space? Okay, probably this question is coming to your mind. So you see, this is a kind of thing which I'm going to tell you, that you have shown that F and F is a vector space. That has been shown in general in chapter 1. N is positive integer. Okay. What will you get? What will you get? If you take F is equal to R and N is equal to 1, then that will become F and F. This will become R of R. So that is also a vector space. Set of real numbers over the set of real numbers is also a vector space. Because in real number, one-dimensional line, we can define distance, etc., etc. All things will be satisfied over here. Try to check it. Try to check these properties. Okay. So this is a special type of transformation where one is V and another is R. You can consider R to be, you can correlate this R to be to that, or you can say that it is a kind of transformation from the vector space to the field. Okay, if you are not satisfied, if you cannot digest it. Okay, so I do not find any point whether you that you will not be able to understand this particular logic which I have shown you just now. So if I can define a transformation like this, if I can select a function, that function is been defined, this transformation has been defined in the following manner. What is this? This is the definite integral. This is the definite integral. You have done lots of problems on that, and you see this particular integration, you have written a to b fx gx dx, that is equal to a to b fx plus fx dx plus a to b gx dx. Okay, you have used it. This is also a linear transformation. So linear transformation is actually giving you a beautiful property in which many special cases which we have done earlier can be considered. So try to go through the chapter, this particular sections once again, and rotation operation, that particular problem, try to show it that it is a linear transformation. After that, in the next class, we shall continue further. So time is running out. Today, I'm going to conclude my session, and you don't have to rejoin once again. So bye for today. Good night.